Okay, let's begin. So for today, we're gonna do everything very specifically in the context of an example. And next time we'll generalize everything. But I think we know all this stuff already, or at least really close. And if you don't know these things, you'll learn them in about 5 seconds, each one of them. We're going to cover a number of different estimation procedures, method of moments, maximum likelihood, and Bayesian estimators. I have said that these are estimation procedures. These two are procedures right here. For Bayes, the procedure is to come up with a posterior. And then we have to talk about which estimator we want to pluck out of our posterior. So the Bayesian procedure is just a framework, I should say. It doesn't tell you which prior to use, and it doesn't tell you which estimator to use. When we get into decision theory a little bit later in this chapter, we'll formalize procedures in the context of objective criterions. So those criterions you're going to have to come up with. So there's nothing objective about it. So there's nothing objective about anything. I'll make that point, but there's reasons why you might want to do something. I'm going to start off in the context of this Bernoulli example. Just a couple notes. I'm going to extend the homework until Wednesday. That'll give you an extra weekend to play around with it. I will run office hours this Thursday at 5:30. So if you guys have any questions, keep in mind, you have to do a little bit of a write-up. I've been open-ended about what that write-up is going to look like, but basically you write down your problem, go through ABC, all of that stuff. The whole thing that you really want to do when you're making comparisons against methods is give me a graphic of some sort that shows how you compare everything. You don't want to give me a table of a million different comparisons. You want something that you can look at real quickly. I can give you some ideas on how I would present everything during the office hours. Of course, it's up to you. Just as a quick heads up, side-by-side box plots, almost every single time. So to compare different techniques. I have another homework assignment that's going to come out probably next week. That's computational. It'll be for the expectation maximization algorithm. That's what we'll be covering next. And so you'll want to get through this because you're going to have another sim study to do right after. And those always take a little bit of time because you have to write everything up, debug your code, make sure your graphics look good. So all this stuff does take time. Saying that, that's what we do as statisticians. That's the name of the game. Bunker?
Oh, no.
Okay. Okay, so back to our example. So from last time we were thinking about this Bernoulli problem, and say we observed a sample that looked like this. Now if you only saw one sample, we wouldn't know what the reason was why we stopped flipping the coin. And so we've got this question mark. Why was the coin, why did we stop flipping it? And oftentimes we don't know the answers to this. We just get to see a sample, and we're not actually running the experiment ourselves. We just get to come in and observe. If, of course, we were running the experiment ourselves, we'd have to have a reason for why we stopped collecting data. So I'll just leave this as a fiction right now that we just observed this and there's a couple question marks. Did I flip the coin 10 times? Where in advance I said I was going to flip the coin 10 times and I was going to stop after the 10th flip no matter what. Or I may have been waiting for a certain number of successes to come around. And so if we're waiting for the 5th success, we would think that this data is negative binomial. If we changed the stopping criterion, we said we're going to stop at the 10th flip the coin, then we're saying that everything is binomial. And there's real ramifications to this, depending on how you do your inference. So I'll just remind us, negative binomial distribution is this, where I parameterized it in terms of the number of trials until the x success. So in our example, x would be 5, there's 5 heads in that sequence. The sampling distribution looks like this. And we derived that last time. So what we did to come up with that is we wrote down, this thing was fixed, it happens with probability p, and then this stuff right here Doesn't matter which order it happens in. There's 9 draws right here. So I'll say this is going to be k minus 1 in our case. K is equal to 10. So that's 10. So 10 minus 1 is equal to 9. So out of 9 draws, I've collected x minus 1 successes. This in our case is going to be 5 minus 1, and that's 4. And so everything is just being sampled in a binomial manner with all these 9 draws. So this is just going to be 9, choose 4, p to the 4, 1 minus p to the 9 minus 4. So that's 5 right there. Then I multiply in this other p over here, and we come up with our final expression, and it's this thing. We talked a little bit about the expectation. The expectation in terms of k can be written down like this, where k is going to go from x all the way out to infinity. So the number of trials that I need until I see x successes, I need at least x flips of the coin. Okay. And you can work out just by going through the sum, and you can probably do that as an exercise. Every time I see these formula, I ask myself, could I derive that? So, and if you can't, sit down and try. So if you can't mentally do it in your head, so I think I can derive this. But that's going to be in any standard textbook as well. We can reparameterize everything. So instead of talking about k, so k is my total number of trials, x is my successes, and y is my failures. So the successes and the failures add up to k in this example. So I can just, in this formula, substitute k. So this thing is k right here. So that's exactly the same. And I could have written this down as x minus 1 down here. So this is going to be equal to x plus y minus 1. And I could write down x minus 1, or I could write down y. They're exactly the same things. So because they're complements of each other. So that's the exact same number right here. And this part is exactly the same over here, but I've expressed everything in terms of the random variable y, which is my number of failures. And so if we wanted to work out the expectation to this, this is just a shift in terms of everything. So I've got this expectation. This is going to be x, the number of successes, 1 minus p over p. And if I wanted to shift everything over to this right here, I just need to shift in terms of x. So I can take this same formula, x, 1 minus p over p, and I can just shift this by x. Keep in mind, this is just a shift when I represent it 2 different ways. So this would be my expectation. Oh, you know what? I've done this wrong. And Anker's about to call me out on it. So this right here, let's get this right. So even I get confused when I do this sometimes, and I have to just think about it. So expectation of y is equal to x, 1 minus p over p. And so if I wanted to talk about the expectation of k, it's just shifted by x units. So this would be x, 1 minus p over p plus x. So that's just my shift. And so you can re-represent this just by writing down, maybe this is x times 1 minus p over p plus 1. So the exact same thing. I'm going to re-express that is 1 over p minus 1 plus 1. So those 2 things cancel, x over p. It's the way you write it down. And that's what Anker said last time, if I remember correctly. So this always is confusing when you're talking about negative binomials with people. It's like, which one are you playing around with? But keep in mind, they're kind of exactly the same thing. They're just shifted. Formula, I guess, looks confusing enough, but it's not too confusing. So I think if you think about our picture and how you represent everything, and that you're using this binomial argument to write down the mass function for a negative binomial, you'll stay out of trouble. Okay, so that's our distribution. Any questions about that? Cool. Okay, now I'm going to just jump into what do you do with all this? How do you estimate things? So I'm going to start out with the method of moments technique. There's a lot to talk about in that technique, and I would say it's fairly unprincipled, but also fairly intuitive, what we're doing. And I'll work through this a couple different ways. But the way we apply this technique is going to differ depending on if we think the data was generated as binomial or a negative binomial. So let's just do this. So let's say I see this sample right here, this one sample. So if I thought everything was binomial, and this is going to be method of moments. And what I should say is this is a collection of procedures. There's an infinite number of ways you can do this. Some of them lead to good answers, and some of them lead to bad answers. And we'll discuss that briefly. I will point out that in Casella and Berger in your textbook, they present a problem where the method of moment estimator gives you a really horrible answer. It gives you an answer that's negative when the parameter has to be positive. And so this technique can go wrong sometimes. So I'd have a look at that example in the book. But I'm going to show you some examples where the method kind of goes right. So if everything was binomial, we know the expectation of x, this is our number of successes, is equal to k times p. And you could derive that. If you can't derive it, go home and play around with it until you can derive all your expectations for all the distributions that we touched. You do this enough times, you'll never forget it. You'll never forget how to do it. That's at least been my experience. So here's the method of moment technique. We're going to say this is approximately x right here. Why? Well, the expectation of x is probably pretty close to what the sample is. So this is your observed sample. So that's what we get. As soon as I make that inequality right there, I'm going to invoke the method of moments procedure. And I'm going to have special notation to deal with this. So I'm going to write down k times p in x, but as soon as I make these things equal, I need to drop a hat on p to say we just defined an estimator. And this is going to be our mom estimator right here, method of moments estimator. So just, at least for the time being, I'll label what my estimators are, what technique I just used. My technique is to match moments right here. So this is the theoretical moment. And I should say this is the theoretical first moment. And this is the empirical first moment.
Should be x bar.
Yeah, but I only have one sample. So x is x bar in this case. So let me do it with multiple samples in a second. So this is our empirical moment. So if you'd like me to sum this, there's no index here, so I only have one thing right here. In our example, this would be a 5, and I could divide by 1 for my one sample. I'm just going to leave it as x. So this means that p hat mom is going to be x over k. And that's kind of a key. This is probably what you would have done in the first place anyway. You might have different reasons for coming up with this estimator. So this is the number of successes divided by the total number of tries. It's a frequency. So it's pretty easy. Let's do it with multiple samples. So this is just the one sample. So keep in mind, my sample was of size k. Let's do this with n samples and see what happens. So this is n samples. And I'll say these are of size k as well. So each sample, every time I go out and I flip the coin, I'm going to flip it. If I thought it was binomial, I'm going to flip it k times, and then I'm going to repeat this n times. So let me just update my picture so we can see what we've done. So what I'm imagining here is that there's going to be n of these. There's going to be k flips n times. It's kind of what we're thinking about. And so, what is this going to look like for my mom estimators? I'm going to write down n times p hat mom is going to be equal to this thing right here, sum of the xi's divided by k. I goes from 1 to k. So that's xr right there. And so that's going to lead to p hat mom is going to be equal to sum of the xi's over k times n. And this again is just the number of successes divided by the number of troubles. So we get the exact same answer if we repeat it over and over again. Let's do it for the negative binomial. So negative binomial. Now the notation's a little bit more cumbersome when we do more repetitions of this. So let's just start with one sample. If we solve one sample, you can't tell if it's negative binomial or binomial. If we see repeated samples, we'd be able to identify this real quickly. Is the vector getting longer or shorter? Is it changing? And is the last element, always fixed to be a heads or something like that? So this is just going to be y. This is my number of failures. My expected number of failures, we write this down, is equal to x, 1 minus p over p, and this is going to be approximately y. I can't write down equals yet. So as soon as I match the moments, then I'll write down equals, but I'll throw a hat on my p. So this is just going to look like x, 1 minus p over p is going to be equal to y, but as soon as I do that, I need to tell you that I've just invoked a procedure. And I throw the hat on top of p. This will usually irritate your statistics professors if you don't throw the hat on p. P is supposed to represent the truth. It's a parameter. P hat is an estimate of that parameter. So you want to be able to distinguish those two things. And then I just need to solve for p hat. So just a little bit of algebra. This will look like y over x is going to be equal to 1 over p hat mom. And I'll just do some mental math real quick. So I've just simplified everything. I divided out p hat. There's a -1 sitting over on this side, so I pulled it over. So if I want to come up with p hat mom, this is just going to be the inverse of this thing right here. So I'll just make the denominators the same, so this is easy to add together. And this is going to look like x plus y over x, or x over x plus y is what you get once you solve this. So sorry for my clumsy arithmetic in my head, but I think you can all do this. So, which is equal to x over k, right here, which is exactly the same thing that we got before. So, and this is the number of successes over the number of failures. Again, we've matched first moments. Hunter.
Isn't it number of trials?
Yeah, that's what I mean. That's what I mean to say. Number of trials. It's the same thing. There was no guarantee that these were going to be exactly the same, but it just happened to be in this case. So this is pretty much an undisputed estimator. Probably use something like this. We can do it with multiple trials, if you'd like. We'd come up with the exact same answer. So I'll say, and I'll let you verify this. For the negative binomial, if you ended up just letting ki is equal to yi plus x, this length of the vector would be changing, the number of failures would be changing. But once you ended up going through the whole procedure, it looks exactly the same as what we just did. You wind up with the number of successes divided by the number of failures. And I'll spare you the arithmetic. If you'd like to see it after class, we can walk through it. But you'll come up with the exact same thing.
Wait, number of failures? Or?
What's that? Same thing, right? Of course. So you'll come up with the same thing. Just by matching this, you'll take expectation of y, and you'll match it to y bar. And that's what you'll just do. You'll come up with that estimate. So this is going to be a function of p. Right here. So when you come up with a function of p, as soon as I make it equal to y bar, then I put the hat over the top. So expectations are always a function of their parameters. Now in the method of moments technique, it doesn't tell you which moments to match. You could match second moments. You could match third moments. You could match any number of moments. You could look at the expectation of a function of your sample and match that thing. If you had p unknowns, p parameters, you would need to match p different moments. We'll go through the multivariate version next time. So which moments would you match? Do you have any guidance on it? Let me just ask you a question. Why would we have matched first moments in this problem? Everything worked out real nicely. They don't discuss this in the book. Nobody tells you which moments to actually match. I kind of like matching the first moment. I like matching in this problem to something that contains the sufficient statistic. So if I just think about what the sufficient statistic is in this problem, I've got my likelihood function. I'll write down, given the data, this is just going to be proportional to p. You could do it like this. We'll do our n sample thing, p to the xi, 1 minus p to the yi, if you like. You just write it down like that. So I could have written the ki's minus the xi's if you wanted to. It's all the same stuff. And so this looks like this. Sum of the xi's, 1 minus p, sum of the failures, I'll write it down like this. Some of the y-i's. And so this right here contains the sufficient statistic. There's your sufficient statistic for this problem. If you're thinking about the binomial case, your sufficient statistic is right here. So that's how it comes in. So if you are going to match moments that contain the sufficient statistic, otherwise you're bound to be making an error. So your estimator should always contain the sufficient statistic. Why? Because that has all the information about your parameter. Again, the sufficiency principle doesn't tell you exactly what to do with the sufficient statistic. It simply says use it. There's another principle in the book called the conditionality principle that says you should always condition on your sufficient statistic. And so in this case, we've done that. So I will point out that in the method of moments approach, we never used the likelihood function for anything. So we didn't use it, ergo, we violated something called the likelihood principle because we didn't use the likelihood directly. Mohammed's going to come in next Monday and give you a lecture on the likelihood principle. To say somebody violates the likelihood principle is a little bit strong because you don't have to adhere to it. How do you violate something that it's not necessary for you to adhere to? Saying that, for me, I do adhere to the likelihood principle. So I don't want to go down this rabbit hole too far because everybody has an opinion about this. So, but I will say, using likelihoods is a good idea. So let me just write that down. And then I'll show you what the maximum likelihood procedure is. So note, using likelihoods, the likelihood functions can be a very good idea. I've shown you a good example where we didn't use the likelihood, we used the expectations. So there's nothing called the expectation principle. So the likelihood function is going to tell you everything you need to know to get all of your moments. It's got all the information in there. Where expectations are just a summary of all the information. So that's where mom estimators can go awry, is they don't use all the information. Give me one reason why the likelihood function is a good thing to use. Somebody give me an excellent reason.
The least MSE.
So maybe, we don't know yet. So it could. So maybe it is going to optimize some criteria. That may or may not be true. So in general, it's not true, but it could in some cases.
It might have some good asymptotic properties.
Good asymptotic properties. Yeah, so a lot of times people will say that things like maximum likelihood estimators are consistent. They're efficient and they converge to the right answer. Saying that, that's not the likelihood function. You did something with it to get a property. So I want to think about just the likelihood itself. Warren.
Because it's conditioned on all the data.
I love that. So it's conditioned on all of the data. Ergo, it's conditioned on all the sufficient statistics. So you're conditioning on the sufficient statistics. So it always includes the sufficient statistic, the whole data set. It could be compressed if you wanted to. You could write it down a little bit different. But I'm just going to say what Warren said because it's conditioned on all the data. Let me just say that again, i.e. conditions on sufficient statistics. So if you use likelihood functions to derive your estimators, you are following the sufficiency principle. So it's automatic for you. So I like that. That's my favorite reason for using likelihood functions. Somebody give me another reason. I like it because in a higher dimensional context, we only have one parameter. But if we had multiple parameters, think about a normal with mean and variance that you need to estimate. I've got the joint relationship between the data and those parameters. So I've got the joint relationship between all of the parameters, and I've got the joint relationship with the data. And so I like using that relationship. And so it preserves all the joint relationships. Between parameters and data. So let me just write down a quick example here. So if we were looking at a normal distribution, sigma e to the minus 1/2 xi's minus mu squared over sigma squared. And I could write that out just a little bit differently. So I could say that's proportional to 1 over sigma to the n e to the minus 1/2 sum of the xi's minus mu squared over sigma squared. And so I've got a relationship between these mu's and the x's. It comes in just like the sample was constructed, so I use that same relationship. And I just flip everything around, plug in my data, and I think about where my parameters are. And I've got the joint relationship between mu and sigma squared. So mu and sigma squared have something to do with each other. So you might be confused thinking that something like x bar and s squared are independent, but there is a dependency sitting right here. I can never factorize mu and sigma squared away from each other. And so they have a relationship. They have a relationship through their data. And this function right here is telling me what that relationship looks like. So it's very important. This part is controlling the asymptotics of everything. I like that. So when we get into Bayes, I'll say this is one of the reasons I like Bayes is because you're using the likelihood function. So there's other things you can do with the likelihood. You could just maximize it. Forget about regularizing your space. Let's just maximize this thing. So MLEs, maximum likelihood estimators, draw you a picture. In the context of our example, where P is going to be between 0 and 1, it's going to be bounded between these two things. So it only has support in those regions. Your likelihood function is going to enforce that. Your maximum likelihood estimator is right there. This is going to be P hat MLE. This is the argument that maximizes the likelihood. So this is arg max over P of your likelihood function. I'll just write it down like this, given the data. This right here is the maximum. So the MLE is not the maximum of the likelihood, it's the argument that maximizes the likelihood. So that's this point right here. Usually in any calculus problem, when you're maximizing something, you want to check the endpoints. So you usually take a derivative, set it equal to 0, solve for that, but you always have to be aware that your maximum could be on the boundary of the space, and you need to check that as well. You probably need to do something like the second derivative test to make sure that you have a maximum and not a minimum. So all that stuff you learned in calculus is still true here. And they discuss it in the book. When they go higher dimensional, they put criterions on the eigenrepresentation of the Hessian matrix, and I'll discuss that next time when we come back. It turns out to be exactly the same thing that you learned in calculus. So you don't need to do the second derivative test per se. I always did the first derivative test, and I would check to the left-hand side of my point and the right-hand side, and I would see if the slope just changed. So you don't really need the second derivative test, but it is an equivalent criteria. Okay, we'll talk about it more generally next time. Let's just do it in the context of our example. The nice thing is, for our example, is it just absolutely does not matter whether or not you think this data is negative binomial or binomial, because they both have the same likelihood functions. That's another reason people like likelihoods, is they're not subject to the stopping criteria. So you don't go awry by using it. They're conditioned on the sufficient statistics, and then that pointy normalizing constant never comes into play. So the likelihood, for our example, for both representations of this problem, are going to look like this. I goes from 1 to n. I'll do the higher dimensional representation where I have n samples. This is going to be p to the xi, 1 minus p to the yi. So I'll just write it out like that. This is going to be my likelihood function for p, given my data. However I've chosen to represent this, it's still the same thing. So if I were thinking about negative binomial stuff, all of my data is right here. The thing that's changing, if I'm thinking about binomial stuff, I'm thinking about that right there. Doesn't matter. Same exact equation, no matter how you think about this. So that's just going to look like p to the sum of the xi's, 1 minus p to the sum of the yi's. So instead of taking a derivative over the likelihood function, it's often nice to take the logarithm first. So why does a logarithm not change where the maximum is?
It's monotonic.
Yeah, it's monotone. So, that's right. So log likelihoods. This is just going to look like sum of the xi's logarithm p. So I've done a little bit of simplification up front, plus sum of the yi's times log 1 minus p. I'm always perturbed by this, that I've got a symbol for proportionality right here with the likelihood function, but I don't have a symbol right here that's generalizable where this can be arbitrarily shifting. So we always just write down equal for log likelihood. But keep in mind, this is equal up to any shift. But as soon as I take a derivative, that thing's constant and it goes to 0 anyway. So we never have to worry about it. But I wish we did have a mathematical notation that kind of matched what we were thinking right here. We don't. We don't need it because it never really comes into play. We never use it for anything. Okay. So when I take the derivative of everything, log likelihood, this is just going to be sum of the xi's over p plus sum of the yi's over 1 minus p, some chain rule, minus. So here's the one part you can get messed up on with a test, is if I go ahead and I set this equal to 0. If you do that, you've invoked a procedure. So that you're maximizing this equation. So we don't do that yet. What we do, we write this down. Then when we set it equal to 0, we throw our hats on everything. And that's our procedure. Kind of like this likelihood business because I don't have to really think about anything. I just operate. So do that typical calculus problem that you start out with either in high school or in your freshman year of college. So sum of the xi's over p minus sum of the yi's over 1 minus p. And here it is. Equal to 0. I'm maximizing, and so I'm invoking an estimator. So at that moment that I set everything equal to 0, I throw my hat on p. And then I can solve for p. Let's see if I can do this. P hat MLE over p hat MLE is going to be equal to sum of the yi's over sum of the xi's. So I'm just rearranging my equation. So I just shifted all this stuff over to the right. Then I divided by xi. I multiplied by 1 minus p on both sides of everything. So this, another way to write that down is 1 p hat MLE minus 1. And so p hat MLE is going to be equal to sum of the yi's over sum of the xi's. I'll add plus 1 right here, and I'll invert this. So I'll change this right here to sum of the xi's over sum of the xi's. Just another expression for 1. This thing right here, once I flip everything over, it's going to be sum of the xi's over sum of the yi's plus the xi's. And at the end of the day, this is the exact same thing that we came up with before. So, number of successes divided by the number of trials. Third time's the charm. Same exact answer. We went about business entirely differently in this example versus our method of moment example. After Mohammed comes in and gives you a discussion on the likelihood principle, you will know the answer to this. But let me just ask you a question. Did I violate the likelihood principle for those of you that did read through it? It's unfair to ask, right? So, for the likelihood method, maximum likelihood, we did not violate the likelihood principle. We used the likelihood principle for deriving our estimator, and most people would say you did not violate the likelihood principle. In our method of moment approach, did we violate the likelihood principle? Yes, we did. And so this is where it gets really sticky, because we came up with the same answer. So the likelihood principle is not about the answer that you get, it's how you went about business in getting that answer. And so you can come up with good stuff if you violate this thing that it's not necessary to adhere to. It helps a lot in fighting. I do like likelihoods because I don't have to think about which moments do I match, does it have the sufficient statistic. I probably have to look at the likelihood function anyway to do all of that. But the method of moments technique is a violation where the maximum likelihood estimator is not a violation, but they're exactly the same answers. So chew on that. Let's talk about Bayes. So just kind of a whirlwind of different techniques, but chapter 7 is the kindest chapter because it just has to work through a whole bunch of different examples. I think that's how you learn this stuff anyway. We'll do a generalization class next time, but let's just stick with this example. So Bayesian Estimator. So what we're going to do for everything is we're going to form the posterior. And this is going to be from the likelihood times the prior. So all that stuff we were doing in the beginning of class, we were making it so this conversation is seamless. We've already done this. I could divide by my normalizing constant, divide by the integral of this thing to normalize everything and put it on a scale between 0 and 1. But really, there's only two things that happens in a Bayesian analysis. You write down the likelihood, then you choose a prior, you multiply it in, and maybe you normalize, and then you pull an estimator out of that distribution. But this is a distribution over P. One of the advantages is just the way you think about it, that this is going to be a probability distribution. So I can interpret it in the way that you typically want to interpret things. So on some sort of probability scale. So I'd say Bayes gives you an easy interpretation of everything, but of course, there's always this calculus problem. So I could write this down, likelihood P given X, pi P, dP. And I'm going to integrate over the whole range of support. But really, all the action is here. This is what controls the shape of your distribution. Let me just ask a quick question. Unfair question again. Does this procedure violate the likelihood principle? And it's a trick question.
Well, you're not.
What's that?
I would say no, because you're not using the likelihood properly.
So what the likelihood principle formally says is that if you have likelihoods that are proportional to each other, you should come up with the same inferences. So that's the exact statement that they give you in the book. You can kind of see it very clearly from the MLE that the likelihood functions are the same. So if I do the same thing with the likelihood, then I should come up with the same inferences. But that's a big caveat that we do the same thing. I'm going to say it depends. It depends on how you chose this and why you chose it. So you can't violate the likelihood principle in picking the prior. So Bayesian analyses oftentimes do violate the likelihood principle. Really, it's a question of how you thought about coming up with your prior. It's not which prior you use, but it's how you went about business in constructing it. And that's why this is all so contentious, the whole likelihood principle framework. People like to talk about it. I even like to talk about it. There's no good. It doesn't tell you what to do. For our problem, if we pick this thing to maybe be a beta half-half, and it would depend on why I picked that, but this is usually a good baseline prior. We haven't gone into all the reasons for that, but if you guys just want to hear, it's Jeffreys, it's transform invariant, it's also reference. It also is your optimal frequentist prior. We'll say more about that a little bit later. So meaning that the intervals that you construct out of it are going to cover optimally. All very interesting. When you do this, we already know the answer, that our posterior distribution is a beta x plus 1/2. This is going to be y plus 1/2. And I guess since we've got lots of xi's in our previous example, I'll put them down as all of our xi's and yi's. The question is what do you do with this thing at the end of the day? So this is some beta distribution. Maybe you maximize it. Maybe you look at its expected value. Maybe you do something else with it. So the expected value for this right here is going to be sum of the xi's plus 1/2 over sum of the xi's plus the yi's plus 1/2 plus 1/2. So this is plus 1. And in your homework example, you've been playing around with this quite a bit, and so this should be almost immediate to you. So I'll just write this down, that this is going to be the number of successes plus 1/2 over the number of trials plus 1. So these are my little regularizers. We almost have the same answer that we had before, but it's a little bit different. As n goes to infinity, we end up converging to the same answer that we saw before. So Bayes is a little bit different. It's like a likelihood game, but we add a little bit to it. The reason this can be a good idea, and you're probably seeing this in your simulations homework, is that when I have small sample sizes, this tends to give you a better answer. So if I have large sample sizes, nobody cares anymore. And so this Bayes thing can do really well when you have a sparsity of data. So in a high dimensional problem, this happens all the time. Even if you've got thousands of data points, if you're in a 1,000-dimensional framework, most of that space is empty. And so regularizing your likelihood is a good idea. So I like Bayes because it does regularize in cases of sparsity. I can include extra information in my filer if I wanted to. I have some notion of objectivity on how to select priors, but what I really like about Bayes is that I'm operating off the likelihood function as the joint representation, and I'm automatically conditioning on all my sufficient statistics. So not a lot can go wrong unless I come up with some really crazy prior. Okay.
So in the Bayes estimator, you're finding the posterior distribution and then constructing the likelihood from the posterior and then maximizing that? Is that what's
Yeah,
happening?
maybe that's what I did. I took the expectation of this thing, and there's a big question as to why. Why is this? Because I could have maximized, and that would give me a different answer than this. They would converge to each other, but this is not the maximum. Keep in mind that a beta distribution can look skewed and all kinds of funny stuff. It ends up converging to something that looks kind of normal. So if n gets big, then those answers will coincide with each other. It'll be very, very close. So the real answer is I need to invoke some sort of a objective criterion. So if I said I want it to be best in squared error loss, that would be my best answer that I could come up with. We have to talk about decision theory and talk what those criteria are. But this is the answer that you invoke if I ended up coming up with a loss function that was quadratic. Chapter 7, later in the chapter, they go through all of this. So I think they end up doing decision theory and then they do Bayes. They talk about what a Bayes estimator is intuitively, but they haven't actually given the specific criteria. So we'll pick up next time with this, generalize a little bit more. I'll say more about the Bayesian setup as well. But I think really the thing that's going to be most useful for us is to work a bunch of examples. So we can see what's going on and then discuss if any violations occur in those examples, so on and so forth. Okay, so that's it for now. Again, I'll be on this Thursday, 5:30 to go over the simulation stuff, anything else you have. But get through that simulation homework as quickly as you can because another one's coming. And it's technically really challenging. So, thanks, guys.